Hello everyone. In first part, we have seen 4-bit and 8-bit RCA using full adder. In this part, we will measure synthesis delay and resource utilization for 4-bit as well as 8-bit adder. 8-bit RCA was created using two different 4-bit RCA, and 4-bit RCA was created using FA. We can look at design sources and we can observe inside 8-bit RCA two different 4-bit RCA, and inside 4-bit RCA FA is visible. It is necessary to keep FA and 4-bit RCA in same project in which we have created 8-bit RCA. Now next we are going to look at how to observe schematic of all these adders. You can observe 8-bit RCA is highlighted, so we can observe schematic of that. In RTL analysis, click Open Elaborated Design. Schematic of 8-bit RCA is visible using two different 4-bit RCA. They are labeled as RCA_1 and RCA_2. Input of RCA_1 is A3:0 and B3:0 as well as C0. With A3:0, X3:0 is connected, and with B3:0, Y3:0 is connected. That is, lower nibble of input is connected with RCA1 and upper nibble of input is connected with RCA2. Over here, for RCA 4-bit and RCA 8-bit, different port names are used so that one can understand that at the time of connecting, if we can take care that which input we are connecting with port of which module, that matters and which is important to generate appropriate output. We can double click on RCA_1. Inside RCA_1, we can observe four different full adder. They are labeled as FA1, FA2, FA3 and FA4. They are useful to generate 1-bit addition. If we double click on any of this FA, then gate level circuit of 1-bit full adder will be visible. Let's click on FA3. Inside FA3, two XOR gate which are labeled as sum0_i and sum_i are visible, which is generating sum. 3 AND gates are there and 2 OR gates are used. Instead of 3 input OR gate, two different 2 input OR gates are used over here. At the time of making modules, when we make FA, we can directly look at its schematic. After making 4-bit RCA, we can observe its schematic and we can perform simulation. Schematics are useful to identify whether our code is converted in appropriate circuit or not. Next, we are looking at project summary. In project summary, project location, top module name as well as the board which we have used is visible. We have selected BASIS 3 Atrix 7 FPGA board. Project summary is useful to identify resource utilization. Post-synthesis and post-implementation utilization in graphical as well as tabular form is available. We will look at post-synthesis utilization in tabular format. In our FPGA, 20,800 LUTs are available. Out of that, 8 are used. In 8-bit RCA, 26 input outputs are used. Out of 106 available IOs. In different FPGA, number of LUTs will be different. So the resource utilization will be different because constructions of LUT, that is number of gates available inside LUTs, are also different. Next, we need to look at timing analysis. In timing analysis also, after synthesis as well as after implementation, timing reports are available. We can click on report timing. Result will be stored as a timing underscore 1 as shown over here. We'll click OK. So after synthesis, timing reports are generated. We can observe timing summary over here. This is our combinational circuit. So most of timing it will show 0 if we click on check timing. But for unconstrained path, because we have not provided any constraint, so over here some timings are available, setup timings for various paths are available. So path 1 to path 9, that is top 9 paths are shown, and it is also shown that from x1 to carry out, total delay, that is maximum, that is 7.005 nanosecond. Total delay include logic delay plus net delay. We can also observe other path like path 2, that is from x1 to sum 6, path 3, that is x1 to sum 7. That means from various input to the different output, whatever is delay that is being visible over here, there are different paths because we were having 17 different input and we are having 9 different output. So multiple combinations are possible. Out of all those combinations, top delay, that is a maximum delay, is shown over here because maximum delay is useful to identify maximum frequency of your circuit. If we look at implementation and if we go for report timing, then after implementation timing will be visible. Compared to synthesis timing, timing after implementation will be little more because after implementation your actual circuit that is connected with your FPGA pin. Let's maximize this timing summary. Again over here we can observe this unconstrained path. Mostly path will be same, like path 1, top path is from x1 to carry out, and you can observe compared to 7 nanosecond, now timing has been increased and it is showing 9.838 nanosecond. You can note down this maximum delay, and based on that we can identify that circuit can function with how much delay, and accordingly we can set frequency when we connect this adder with some other circuitry. Using similar methodology, we can create multi-bit adder circuit. Block diagram of 32-bit adder is shown over here. We can use 8 different 4-bit RCA to make 32-bit adder. I am sure this video is useful to create 32-bit, 64-bit or even 128-bit adder circuit. Thank you very much.